Hello everybody, welcome to my office. Now that everybody's kind of gone, they just left me with Dumbledore's digs, so I got the best place in the house. But no, in all seriousness, today we're going to be doing our second lecture in second order differential equations. This is the main lecture. We're gonna have I think two little extra videos that come off of this. And I think this might be the last video that we're going to be doing in second order differential equations. I want to prioritize getting to deal with models of the spread of disease and epidemiological models. So because of that, I'm going to trim a bunch of stuff out that tend to just be specific examples from physics, or really forced and artificial mathematical, like, hey, if the functions look like this, here's a method you can solve it. And so that to me is not nearly as interesting. Okay, so if you remember from the last videos, we were studying a second order constant coefficient with a non-homogeneous part f of t at the end. And what we basically did was we said, hey, to solve the homogeneous problem, you just use characteristic polynomial. So the ansatz solution, supposing x of t equals e to the lambda t, plugging it in and finding lambdas where you weren't a liar. And then to find that f of t for the full problem, the particular solution, what we did was basically the method of undetermined coefficients, or guess and check. Pick a function that's similar to that forcing function, plug it in, and again, see what constants have to be true so that you're not a liar. Okay? Pretty straightforward and self-explanatory. All right? In this situation right here, we're dealing with a much more general set of equations, in that if I look, the P and the Q, my finger can't reach that far. It goes into the void. Those are non-constants. So now those are functions of time. So the forces that they represent, like drag and friction, or restoring force, or spring force, or gravity, or things like that. Not gravity, that was stupid. But those can vary over time, just like our forcing function could. Okay? Now, as a rule, even though these equations are still linear, the x's aren't kissing any other x's. They're only kissing functions of time. You cannot solve these using what we would consider familiar functions. Okay, there's these things called special functions, and I'll put a couple links below. You can really just Google them and you can find a bunch of information, but I'll put some links below of some sources that I like in the description that come about through solving equations like this. Okay, but what is nice about these equations, mostly because they're linear and all these nice stuff, we still have existence uniqueness, and we have the linearity principle. Okay, so to break down again, in brief, what those things mean. For existence and uniqueness, if I think about the solution across the time axis, there we go, my solution x, if we have an open interval I, and we have any initial time point, let's say t0. Okay, if I know the value of the function at that time and its slope, then I can say over that interval I, there exists a solution to this differential equation, and it is the only solution that passes through that point. I'm not going to have any solution curves crossing, which is fantastic. We still don't like to have that, okay? And I can actually go through the endeavor of solving it. Now, if you wanted to extend that over, like, let's say all of time or whatever, you just basically keep considering new open intervals where you have new initial conditions, basically like where you end or somewhere where those intervals overlap, okay? Pretty straightforward. Now, the linearity principle, if you remember, this tells us about the solution to the associated homogeneous problem to this, as well as how to combine those things for the general solution of this differential equation. Okay? So the homogeneous solution says you're going to take a linear combination of two independent solutions, x1 and x2. Now, linear combination means those x's, they don't kiss each other or any other x's, and they just have those constants, c1 and c2 in front. Okay. Now, if you take any particular solution that happens to solve this, okay, then our general solution to that equation is the homogeneous plus the particular solution. We can still do that. That's fantastic. Oops. Now, in all of this, my hands are invisible. It looks pretty much like the same thing, except for these equations, it's really hard finding the x1 and x2. Okay. So let's go through a process called variation of parameters. It's similar to method of undetermined coefficients, but a bit different. Okay. Again, we have our general problem, which I'm doing in red, and then in green is the associated homogeneous problem. Now we are going to suppose that we've already found a function x1 and a function x2 that are independent from one another that happen to solve the associated homogeneous problem. So we're just going to pretend that we have those for right now. Okay. then what we want to do is to say, well, how can we put these pieces of information there? Okay. What we would normally like to do, which we've done before, is sort of like, hey, we can find the characteristic polynomial in order to find these x1 and x2s, and that gives us something to hold on to. Problem is, this doesn't work. Okay. So I'm going to make a video about why that doesn't work, but you can try it, plug it in, you'll come up with like sort of a logical conflicting piece there, contradiction that you can't move through anymore. Okay, but now if x1 and x2 are solutions to the homogeneous problem, I want us to consider x sub p to be u1 of t x1 of t plus u2 of t x2 of t. In a lot of books, those u's are c's. I find it gets confusing, but what's important is there are two unknown functions, u1 and u2. And we're going to propose that the solutions to the homogeneous problem, I can now make a combination of those that's not just constant coefficients, but some unknown functions, and it's up to us to figure out what those functions are. Okay, so to go through basically the same exact game we've been playing over and over and over of saying, hey, is this a solution? Well, plug it in and figure out how you're not a liar. All right, so if that's my xp and I want to plug it into this red function here, I need to find xp prime and xp double prime. So that's our goal right now. So if we look here, xp prime, we're just going to use the product rule. u1 prime x1 plus u1 x1 prime plus u2 prime x2 plus u2 x2 prime. Cool. Now, xp double prime, which you can see is taking me a while to write because there's so many terms. We're doing the product rule to each of those four terms that's in xp prime. It is important for me to do out all these details because I feel like it's important for you to really get a feel for what's going on. And we are playing a very important mathematician's game in doing this. Okay. Anyway, doing all those derivatives, you get x1 double prime, u1 double prime x1 plus u1 prime x1 prime plus u1 prime x1 prime plus u1 x1 double prime plus u2 double prime x2 plus u2 prime x2 prime plus u2 prime x2 prime plus u2 x2 double prime. La, 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 la. Take all these expressions right here. Okay, we're going to plug it into the red expression. Right? And then what I want to do is I want to group by the unknown functions, the things that we are seeking, the u1 and u2. Okay, that's our goal, is to figure out what those things are. And so that's what we're going to do. Okay, so plugging those things in and grouping them, I can see first off in all three of these, the only u1 double prime is touching an x1 prime, or x1. Awesome. The only u1 prime is touching. I see I've got two x1 primes from this equation. And then xp prime is going to be multiplied by p of t. And so I get a p x1. And the u1s, right here I get an x1 double prime. Right here I get an x1 prime, but that's going to be multiplied by p. And right here I have an x1, but that's going to be multiplied by q. All right. And so we get all of those. That's all my u1 terms. Now, effectively, we have all the exact same u2 terms, except they're touching x2s now instead of x1s. Cool. So we're going to write that down. I feel like I should turn up the music for this. I don't even know what the music is right now. Watch it happen. Cool. When you got all those things written down, all of that has to equal f of t because we plugged it into the red equation. Okay, so this is pretty awesome. Look at those parts that I'm highlighting in green. Look familiar? Right? Those are the exact same form as the homogeneous equation that we assumed x1 and x2 were solutions of. So because of that, those two terms right there that I highlighted in green, those are zero. That equals zero because x1 and x2 solve the associated homogeneous problem. All right, so those two terms go away. And now what we're going to do is just, again, a little bit of massaging, a little moving stuff around, okay? u1 double prime x1, u2 double prime x2, plus 2 u1 prime x1 plus, u1 prime x1 prime plus u2 prime x2 prime, close that off. And then all that we're left with at the end is p, which is p of t, remember, x1 u1 prime plus x2 u2 prime, okay? For some reason, I'm taking forever to write this. There we go. Even though I got the new stylus, my handwriting is awful on these things. Bear with me, okay? And all this still needs to equal f of t. Now, this is what we have to work with. Now, here is the game that I'm saying we're allowed to play. We need to figure out and find what u1 and u2 are. Okay, and we can see that they turn up in the equation as second derivatives, as first derivatives. Nowhere does it show up as u1 or u2. What we get to do is decide what are the rules behind u1 and u2. And as long as we don't ever construct a contradiction of any kind, we're going to be a-okay in doing that. Okay, so because these sheets are a little small, I took some time to rewrite it. It's again Dumbledore's office. I like how my writing always goes up to the right. That's an x2 for the record, right there. That's an x2. Okay. Now, if we look at this equation, I've highlighted there in purple basically the ugliest part. We have p of t, which is some known function, right? It can be big and ugly. It is complicated as whatever. Okay. We have x1 and x2, which we know are solutions to the homogeneous problem. Why don't we let this be 0? Now, I'm not saying let p of t be 0 because that can't happen, but I have the freedom to choose information about u1 and u2. So why not u1 prime x1 plus u2 prime x2? Why don't we let that equal 0? And we're going to call that rule number 1. Okay, why can I do that? I haven't set that u1 or u2 equals 0. They are some function of x1 and x2, clearly. Okay, now what can we infer from that? Well, basically, if something equals 0 everywhere, then we know its derivative equals 0 everywhere. We know that for a fact. I can take the derivative of that expression, and I get u1 double prime x1 plus u1 prime x1 prime plus u2 double prime x2 plus u2 prime x2 prime, and that still has to equal 0 because the derivative of 0 equals 0. Now, why would you take the derivative of that like this? Because you spent a lot of time, and you noticed some of the terms were already present. As a matter of fact, you noticed all the terms were already present in that above equation. u1 double prime x1, that's right there. u1 prime x1, well, half of that, because there's a 2 in front of that term, is right up there. u2 double prime x2, that's right there. And u2 prime x2 prime, again, half of that is up there. So just by rule number 1, if we take rule number 1 and stick it up into the here. So rule number 1 is the only thing that we've said, hey, why don't we let this be true? If that happens to be true, then all that blue stuff vanishes, and we're left with u1 prime x1 prime plus u2 prime x2 prime must equal f of t. This is basically our second rule, right? And it's a much simpler expression than what we started on previously. Okay, take a look at it. It's god-awful. Right? What's important about these two rules and why we can use them is we weren't faced with the situation where rule 1 implied rule 2. The fact that the two rules are in some sense independent from one another. Basically, if I had used rule 1 and the next line, those two things say basically the exact same information. There's a little bit more information that can be, or rule number 1 is a little bit harsher than the line underneath it. But because rule number 1 has to pass through basically this function up here in order to get to rule number 2, they're independent from one another, and we can't just go back and forth between either of them. One does not imply the other and vice versa. So I'm going to take a little bit of time, okay? And I want to write down this expression very carefully. So what I'm doing right now is I'm going to write down rule number 1, and directly underneath that I'm going to write down rule number 2, right? And the reason I'm doing it like this, well, first off, I'm going back and forth because I'm terrible at planning spacing. But I want us to note, what do we know out of both of these rules, and what do we not know? All right, so I look at that. I don't know what u1 prime is, because I don't know what u1 is. I know what x1 is. We assumed it was some solution to the homogeneous problem. Let's say we've got it. Okay. I don't know what u2 prime is, because I don't know what u2 is. I know what x2 is because it's a solution to the homogeneous problem. I said we had it. I know what the number 0 is because it's the number 0, and I know what that is. Okay. And finally, I know what x1 prime and x2 prime both are, because I know x1 and x2, we can all take derivatives, and I know what f of t is because it's in the statement of the problem. Okay, right there. Statement of the problem. Okay, x1 and x2, given solutions. F of t, statement of the problem. There. I got a little ahead of myself and I don't feel like editing videos. Go back up. Okay, so what we're left with here is we have two equations, right? And two unknowns, the u1 prime and u2 prime. And they're linear in u1 prime and u2 prime, in that if you think of that thing, they don't kiss each other. There's no multiplication there. We don't have u1 prime, u2 prime. Nothing like that. Two equations, two unknowns, they're linear. We can solve it. And that's essentially what we're going to do. It looks a little ugly. I'm terrible at using up such a small amount of space, so it's going to get a little squishy here. But what I'm going to do, let's go ahead and get rid of the u2 primes first. Okay, so we're going to notice that that first equation's term, u2 prime x2, is missing an x2 prime when I compare it to the one on the bottom. So let's multiply the entire first equation by x2 prime and the entire second equation by x2. And then subtract them. So what am I left with? I'm left with u1 prime. I start so nicely there, so well written. x1 times x2 prime minus plus, completely ignore me, x1 prime x2 equals negative. Did I make a sign mistake? I 100% made a sign mistake. I'm just noticing it now. That plus is supposed to be a minus, and still didn't fix it there. Cool. I have a really hard time with this fraction right here, so bear with me. Anyway, if that's a minus, that's going to equal negative f times x2, because that's what we have to multiply the second equation by. Take all of this and solve it for u1 prime. Okay, we're going to assume that the minus sign was there down in the denominator, but it's not, and it'll be better defined right there. But now if we look at the right hand side, that's all a function of time, and the left hand side is du1 dt, so I can just integrate both sides with respect to t to get my final answer, right? Because I know f, I know x2, I know x1, I know x1 prime, I know x2 prime. Those are all functions of time integrated. Okay, so u1 is going to be equal to negative. Now, right now I'm writing down the antiderivative of f of x2. Look at me fix the sign right there. x1 x2 prime minus x1 prime x2 dt. Okay, now this all right here, we've just solved the first unknown function, which will be the coefficient in front of x1 in my particular solution. I need a little bit more space, but we can essentially do the exact same thing to find u2. All right, so we get, again, write down the two rules that we had. u1 prime x1, let's go and multiply that by x1 prime, plus u2 prime x2, x1 prime, equals 0. And then my second equation is going to be u1 prime x1 prime, there we go, plus u2 prime x2 prime x1. Put a prime on that x2. I'm going to do it eventually. Equals f of x1, because I took the entire first equation, multiplied it by x1 prime, and the entire second equation, multiplied by x1. Okay, taking the difference, here's where I'm going to notice that I left out the prime. Okay, taking the difference and then solving for u2 prime, I get f times x1 equals x1 x2 prime minus x1 prime x2. And again, integrating both sides because it's just a calculus problem now. I get the antiderivative of f times x1 divided by x1 x2 prime minus x1 prime x2. All that is integrated with respect to t, or time. Okay. Now, this is a lot. My mouth is dry. I've been talking forever. Okay, but here we've got our second coefficient, the function of time, that's going to go in front of x2. And it's important that you put these in front of the right ones, because your x1 has meaning and your x2 has meaning now throughout this whole process. Now you look at those denominators right there. That denominator has been repeated. It is a nice function that we often write as w of t, and that stands for Wronskian, which is named after a mathematician. I think Rons was the last name. All right, and it's got a very nice form. It's sort of product rule-y, feely. It's a determinant of a particular type of matrix. It's very interesting. And yeah, I kind of like it. It's kind of neat. I wrote it wrong. The derivative's on the wrong spot there. It's on the x2 in the second term instead of the x1. Wow. Totally missed it. I'm tired. Should probably edit that. Completely reshoot this video. I'm going for like 20 some odd minutes now. I'm not sure if I want to. You'll notice right here now that I'm placing it into the function for xp. I'm putting bounds on those intervals from 0 to t. And I'm just replacing those t's in there with the dummy variable of s, just so that it makes me feel good. But essentially now, if that's my homogeneous solution, c1x1 plus c2x2, then my particular solution is going to be equivalent to this u1x1, u2x2, where the u1 and u2 are defined that way, and the Wronskian's actually defined correctly. I think we're all set with this. Just to triple double check, my Wronskian, that is x1 x2 prime minus x1 prime x2. Okay, made some mistakes. We learn from mistakes. Have a good one. We're going to have 2 short videos that are coming up after this, where I go through an example of how to calculate the Wronskian and use it in a problem. And, oh yeah, why the characteristic equation is bupkis here. All right, see you guys around. Where's the book?